Bay Area, where he transferred from where were you?
Foothill College.
Foothill College to University of Montana a few years ago. And the last couple of summers, he has been a student, summer student through the Montana Space Grants Space Science and Engineering Laboratory in Bozeman, where they basically farmed him out to 406 Aerospace, which is a private aerospace company in Bozeman, where he has been doing his summer research. So with no further ado, Ryan will be talking about that.
Thank you, Dr. Esquivel. You're welcome. Now, satellites. When you think of this word, images of large engineering marvels pop in our mind of giant pieces of metal orbiting around the planet, and maybe about the size of your car, so 15 feet long. But as we all know, satellites get much larger than this. So one of the most famous ones we know is the Hubble Space Telescope, which has been orbiting us for over 24 years now, taking deep space images of the cosmos. And the satellite has really captured the hearts and minds of the world because of what it's shown in this. And the Hubble is 43 feet long, so we're getting a little bigger here. And Ryan, what could be greater than 43 feet long? What's taller than a 3-story building? Well, International Space Station. As we all know, this has been up there for 16 years now. It is 239 feet long, 356 feet wide, and 63 feet high. And that right now is about the pinnacle of what we have built in size of satellites. Now, many satellites these days can cost upwards of hundreds of millions of dollars to design, build, launch, and maintain. But say, for example, what if these costs could be less? What if you could miniaturize satellites? Well, that's where these guys come in, cube satellites. Little 10-centimeter cubes that can cost, only maybe at max $100,000 or so to build and do everything. This seriously opens the qualifications for who can build and launch their own satellites. Notably, smaller countries, companies, and most importantly for this talk, universities. If universities can build their own satellites, then they can conduct their own space-based missions. Now, where did the idea of cube satellites come from? It originated in 1999 during a collaboration effort between two teams at Cal Poly San Luis Obispo and Stanford. The two leading professors, Jordi Puig-Suari at San Luis Obispo and Bob Twiggs at Stanford, wanted to see if they could produce satellites that universities worldwide could then use for their own space science and exploration missions. At the time, they were working on a project called OPAL, or Orbital Picosatellite Automatic Launcher. But there were several problems with this mission. One, the launcher itself wouldn't launch the satellites every time. The launcher is the device that cube satellites are placed in when they're launched up, and then once in space, they're launched out of the launcher. And as you can imagine, if it doesn't launch all the time, that's not good. The other problem with this was that picosatellites, due to their small size, was not very conducive to solar panels. Picosatellites are even smaller than cube satellites, having dimensions of 10.1 by 7.6 by 2.5 centimeters. And just due to that small size, it was just too small. So Bob Twiggs in particular wanted to see how small you can make a satellite while still being able to place solar panels on it. He came up with the idea of the cube satellite after seeing a 4-inch plastic box that was used to display Beanie Babies. He presented this idea to Puig-Suari during the summer of 1999, and he loved it. They then presented it at the Japan-US Space Science Conference in November of 1999, and the idea really took hold. Within a few years, the first cube satellites were launched in 2003. Now, to date, more than 75 have been launched, with many more on the way. Now, these here are some examples of some current satellites that are orbiting us right now. Herbie is actually a locally made satellite, since this was produced out of Montana State University and was used to study the Van Allen radiation belt around the planet. And M-Cubed is a satellite launched from Michigan State to take mid-range resolution photos of Earth. They were both launched in the same launch in 2011. And funny story behind these two satellites. Now, most satellites have small magnets in them so that they could adjust small degrees of, they can change their position slightly, such as pitch and yaw. Well, they got too close to each other, and then they got stuck to each other. So now if you're tracking that satellite up in space, you're actually tracking these two stuck together. Now, due to the advances in rocket technology and CubeSats, CubeSats can now be launched from a variety of different platforms, including SpaceX, Atlas, as well as other domestic and foreign rockets. And this right here is an image of CubeSat launcher in space being launched from the International Space Station. And as you can see at the bottom here, there are 3 little CubeSats. And a video here of CubeSats being launched from the International Space Station. Why is that not? It's not right. Why did I apologize for these technical delays. I don't know why that wasn't working. Well, I guess I'm gonna have to skip the video there since it's not working right. But anyway, in the video, it was going to show the satellites being, it would show the docking mechanism on the launch opening and then satellites being launched out. And in the video, you would see CubeSats called 3U satellites, CubeSats. CubeSats come in 3 different sizes. There's the 1U, 2U, and 3U, standing for 1 unit, 2 unit, or 3 unit. And they're just basically the size of 1, 2, or 3 units built together.
There's also 1.5 units, too.
Oh, didn't know that, thank you. Although somehow I'm not surprised. Back in the summer of 2013, I was an intern at 406 Aerospace, which was part of a larger mission commissioned by NASA titled PONSD, or Proximity Operations Nanosatellite Flight Demonstration, which wanted to deal with 3 main goals. 1, to validate the use of new sets of low power and smaller pieces of hardware and components, as well as new software approaches to control these devices. 2, deal with proximity operations between the 2 satellites, so dealing with different distances between them from optimally 0 to 25 kilometers and under different lighting conditions. And thirdly, deal with practice docking between the 2, so dealing with safe approach vectors between the 2 and docking safely. And with these 3 missions, the first one is pretty obvious for CubeSats. The whole idea behind it is to miniaturize satellites and thus reduce costs so that more people can do it. And if you can reduce the size and thus the cost of components and the way that you control them, you can seriously reduce the cost. The second and third mission goals kind of work hand in hand. They're dealing with new jobs for CubeSats. Say, for example, you have a larger satellite that's that ground control has lost contact with, or it's not accepting commands. The CubeSat could be used to dock with the larger satellite and then connect with it and then relay instructions or software updates to the larger satellite, hopefully fixing it. Potentially, maybe the problem's bigger than that. The second job is that it could do reconnaissance on the larger space vehicle, orbiting around it, taking images of it, and identifying if there's any hardware issues or anything that's broken with it. And with the lighting conditions, let's keep going. Now this is a schematic of the flight plan. Now I don't want you to think that it was going into a suborbital flight, in that it was being launched and then go into a suborbit and then fall down. The 2 sides would go into a low Earth orbit. Now they will be launched together, either held together with their magnetic grapples, or held together with explosive bolts. Either way, once in space, they will detach and begin running formation flights. The first flight is the proximity flight, where let's call this satellite A, and this one's satellite B. Satellite A will continue on with its current orbit path, and satellite B will fall back behind to a certain distance. Once it's fallen behind enough, it will use its propellant to then enter into new orbit and catch up to the first satellite. It will then orbit around the small satellite, taking images of it, and then they will switch roles. Now this will be done numerous times from different distances as well as lighting conditions. And by lighting conditions, I mean the satellite will be the B satellite will have to catch up when it's either full sun, full darkness, sun in front, sun behind, or combinations of the two. Once this maneuver has been done, they will practice docking with each other numerous times. Once all the formation flights have been tried out, the two cube satellites will then fall back to Earth and burn up upon reentry. And they will probably stay in orbit for about 5 years or so. Now, as I stated earlier, I was an intern at 406 Aerospace, which is a small startup company in Bozeman that works with Montana State University, as well as other colleges and companies around the country to build cube satellites. Their part in this mission was to test out and use infrared imaging equipment that will be used to identify the other satellite, as well as inter-satellite communication devices that will be used to allow the satellites to communicate with one another. Now, there were a number of goals expected of us interns. First and foremost was we needed to learn C# programming language, and with this, make a edge detect, object comparison, and edge detect with object comparison programs. We're also expected to learn how to use STK, or Satellite Toolkit, which is an advanced modeling software that's used to model satellite orbit paths in our case. We also needed to test out numerous different types of wireless communication chips with different frequencies, bit rates, and antenna combinations to see which would work best for our mission, as well as take numerous images of CubeSat models such as this and use these in our test programs. Now, edge detect is much like the way it sounds. It takes an image and breaks it down to edges of the image. It looks specifically for sharp points in the image where the colors in the image change sharply. And it does this with one of two ways. One is a search-based algorithm where it takes the first derivative function of the image and looks for local maximas in that first derivative. The second is called zero crossing, where it takes a second derivative function of it and just looks for zero crossings in that. Once the image has been taken and it goes through the edging, filters are then added to determine how sharp or smooth the resulting images look like. Object comparison is also much like how it sounds. It takes one image and compares it to another image or sets of images in the database. One approach that is done is a pixel approach, where it identifies each individual pixel in the picture and tries to max them up. And depending on the pixel tolerance that you set, it will determine to either be a match or not. Another method, which is much faster but much less accurate, is a histogram approach, where it just takes an overall histogram, color histogram of the images and compares those. But as you would expect, that's highly inaccurate, because if you then take a second picture of the same object, let's say the object has been rotated or is in a different light, the histogram will most likely record that it's not a match. Now, SDK, as I said earlier, is called Satellite Toolkit from a company called AGI. Now, this modeling software is used extensively by NASA and its partners, which is why we were able to use this in our mission. Here's an image of the satellite as well as the Earth, and it's an incredibly detailed software, because the models themselves are really nice. And then the cool part of this program is that it overlays on top of Google Earth. So you not only get a detailed image of whatever object you're modeling, but of its perspective on Earth as well. And this here is an image of an example of what orbit paths can look like on STK going around the Earth. Now, in regards to satellite imagery, they usually fall into one of three categories. Either taking images of Earth, as you see in Google Earth or Google Maps, 2, taking images of nearby satellites or objects in orbit. Or 3, taking images of far-off astronomical objects, such as what the Hubble Space Telescope does. Now, in regards to what we were dealing with, we didn't have to take pictures of planets or galaxies. We didn't have to even go as far as the Earth. We were just taking close-up images of a satellite no more than 25, hopefully no more than 50 kilometers away. And for this, we were given infrared cameras from a company called FLIR. For those of you who've never heard of FLIR, it's a leading company in the field of infrared imaging. We were dealing with the Tau-2 model camera, which sees in the long-wave infrared spectrum. This is looking in the spectrum of 8 to 15 micrometers. And this means that it identifies objects that are only slightly higher than passive room temperature. It also had a wide field of view or narrow field of view, depending on what we wanted. And then I had the dimensions here listed at the bottom to give you an idea of how small these cameras are. Now, note the dimensions here are just of the camera itself without the lenses. So that small camera would have to fit into this little tiny cube, which, judging by the dimensions, is a pretty good chunk of it. And the mass of the camera was 100 grams. This is important because the overall capacity of the Cube satellite in this mission could be no more than 1 kilogram. So in the end, this camera is 1/10 of the total mass, which really shows you why miniaturizing and getting components down to as small as possible is really important in the Cube satellite program. And these here are just images of the Tau-2 camera with 25 millimeter and 50 millimeter lens. So you imagine once you put these lenses on, you add a lot more mass and even more size to it. Now, in order to take accurate photos or accurate test photos of the Cube satellite model, I used the hallway in our building. I did this for 3 main reasons. 1, I could accurately determine the distance from camera to Cube satellite by marking up the floor with blue tape. 2, the hallway was incredibly cold, so the hot Cube satellite really stood out and took really great images. And 3, there was minimal foot traffic, so there was, I didn't get much interference with my image taking. The only problem was that each session of photo taking took about 20 to 25 minutes. Now, this wasn't 20 to 25 minutes of constant photo taking. This was 15 to 20 minutes of the Cube satellite heating up outside, and then 5 minutes, if I'm lucky, of the taking pictures. Because as you can imagine, a hot piece of aluminum like this in a cold hallway really is going to radiate the heat quickly. In order to solve this, I thought, well, let me think here. It's Bozeman in mid-July. Every day it's getting to the mid to upper 90s. It's really hot out. How can I get it even hotter than just outside? Well, my car gets really hot. So I just stuck this little guy on the hood of on the dashboard of my car. Within 5 minutes, the thing got super hot, and I actually burned my hand the first time I tried to get it out. So I learned, use a sweater next time to move it. And with that, I got fantastic images, which I'll show you now. These show up. Oh, you gotta be kidding me. Now you do it. Why is that not?
Can you drag it from that screen to that screen or something?
Let's see if that. Oh, there we go. So these are images taken in the hallway. This was done with a 25 millimeter camera at 2 meters. You can see really nice detail and really nice edge work to it, so you can really identify what side you're looking at. And you have the solar panel side here, also at 2 meters with 25 millimeter. And you can even see the slight outlines of where the solar panel is on the Cube satellite there. Next up here is with the 50 millimeter lens, and this was taken at 1 meter. And as you'd expect, with the larger lens, the level of detail in this is even greater. Unfortunately, in space, we won't have these nice little gaps to look through to identify what side we're looking at, because it will be full. This was done at 20 meters with the 50mm lens. And even at this distance, even though it's a little hard to see with the projector, but you can see the edges of the Cube satellite really well with this, despite the distance, which is key when they want to try to identify the approaching Cube satellite in space. And this is just a close-up with the 50mm lens at 1 meter. And a funny note about this: we were working with 2 different Cube satellite models during the project, and the images taken here are different from this one. So I guess they sent me the other model. Okay, in regards to inter-satellite communication, this is how satellites talk with each other and exchange data and information. First and foremost, it's used to network between satellites so that they can exchange information or data with one another. And probably the most common thing shared in space is communication data. So when you're making a call on a satellite phone or any other type of communication device that uses satellites to bounce around the world, this is how they do it. It's also used to broadcast their individual positions to one another so that they can tell with respect to one another where they are, so that they don't get too close, and things like what happened to Herbie and M cubed don't happen. This here is a list of the wireless communication devices that we were working with. We were given Zigbee Pro 900 HP chips to test out a number of different frequencies and data rates. It's important to note that the 200 kilobits per second 900 megahertz chip was ranged to 4 miles or 6.5 kilometers. The 10 kilobits per second chip was rated to 9 miles or 14 kilometers. And the 2.4 gigahertz chip was rated to 2 miles or 3.2 kilometers. Now with the 3 kilobits chip, it had a U.FL RPSMA and wire antennas. And you're probably wondering, what in the world are those antennas? Well, luckily I have nice images here to show you. The U.FL antenna is the one here shown on the lower right. It's a normal sized antenna for its class, which is about 4 to 5 inches in length. It's like most antennas, except instead of attaching to the chip directly, it has this long wire that then attaches to the chip. The RPSMA antenna is the one here shown in the upper right. It has a female end that then connects to the male end on the chip. And the wire antenna is just this one right here. It has a small integrated wire that was about 1.5 inches long. And the SMA antenna looks almost exactly like the RPSMA antenna. The only difference is that with the RPSMA, there was a little pin on the chip end, while in the SMA, the little pin was now on the antenna end. Now, there was no difference in functionality between the two. They just did this to comply with regulations. So, and then the 2.4 gigahertz had an RPSMA antenna. Now, before I actually get into the data taken with these chips, I need to explain a little bit more about the axes and what we're actually gathering. Now, RISI is the received signal strength indicator, which shows in decibels the amount of signal strength or power being received by the antenna. Now, let's note that all of the signal strengths we were getting were all negative values. Now, this doesn't mean that we were getting negative signal strength, because that would be impossible. Instead, decibels is a logarithmic-based 10 representation of the power or intensity of the signal that you're receiving. And I have some examples here of different wireless devices that we see in our everyday life. At the top here, 80 decibels for an FM radio station, negative 10 decibels, which is the typical max power received by your wireless network, and all the way down to negative 127 decibels for the power received from GPS satellite. Now, note, this isn't the power being transmitted from the satellite. This is the power that you're getting, say, on your phone or any other device that has or that uses the GPS. Also, when you're testing chips and you want to try to push them to their maximum distances, you have to cut out interferences with the signals. There were 3 main sources of signal interference in our tests. One was signal reflection, which is where the signal given off by your antenna bounces off the ground or nearby objects and then interferes with your original signal. The second is any wireless device that broadcasts at a similar frequency that you are will cause interference of some kind. And possibly the largest source of interference, apart from line of sight, so going through brick walls or something, are electrical devices such as power lines or power stations. These can cause major sources of interference and should be avoided at all costs. Now this is a picture of our first test location on Nash Road, which was a road just east of Bozeman. It was a perfectly straight stretch of road with a really nice dip in between it. And a dip in between test locations is important because this helps reduce signal reflection interference. And then because we're out in farm country a bit, this really cut down on electrical device interferences. And here we were testing from 0 to 2.5 kilometers. Now this here is a graph of the data that we took on Nash Road. It's a little hard to see the key on the top there, so I didn't do this graph. But at the top here, the solid blue line is the 2.4 gigahertz. The red line is the 900 megahertz at 10 kilobits per second. The yellow is 900 megahertz at 200 kilobits per second with the female antenna, and that was the U.FL one, so that was the one with the wire. The green is 200 kilobits with the male antenna, so the RPSMA antenna. And then all the way down here on the bottom is the 900 megahertz chip with the wire antenna. As you can see here, the wire antenna just performs awfully at long-range distances. It begins cutting off dramatically from the very beginning, which showed us that we really can't use this for long-range distances at all. It's used for close distances, probably for ranges less than 400 meters. Then at the top, you see the remaining 900 megahertz chip perform very well up until about 1,400 meters, about 1,400 meters. And then the 10 kilobits per second chip begins really dropping off, while the two remaining 900 megahertz perform roughly the same to 2 kilometers. So we'll have to test those at longer distances. And the 2.4 gigahertz has a similar line function to the others, but as you can see, performs in a lower signal strength from them, which was to be expected because lower frequency chips can travel further than higher frequencies because higher frequency radio signals are more easily and quickly absorbed by molecules in the air. Now this is a picture of what I call the rig. This is how we took our testings for like what you saw in the previous hits, because we couldn't just walk out 2 kilometers. That would take all day to take just one set of data. So we set up the chips on top of these large 6-7 foot tall PVC pipe stands with the chip and antenna on the very top. And then because I was the only one with a sunroof, I was nominated the guy who drove back and forth all day. So I just stuck that in between my chair and center console and drove around. I just had to make sure I didn't go too fast, otherwise the antennas sometimes wanted to fall off. This is where we did our long-range testing, which was from 0 to about 7 kilometers, where we placed one team on top of the Bozeman end and another team out 7 kilometers west along Highway 90. I'd like to say that with the following graphs, there are some changes to it. Not only are we looking at signal strength now, but we're also looking at what I call percentage of packets. Now, these are two completely different signals. The signal strength is an analog signal, and the packets is a digital signal. Analog is a signal where it's just a constant sine wave, and it's can be a lot more complicated because it combines all the data in that signal, which is why it steadily decreases over time. However, digital signals are much simpler. They're comprised most of the time just out of segments of zeros and ones, which are then interpreted at the receiving end and turned into more useful and readable data. This is why you can get really good digital signal results out to a certain distance and then just drop off, because this represents the maximum distance that it can go. As you can see here with the 10 kilobits SMA antenna, this goes out really far. It goes about to 2,500 meters and then begins dropping off. There's one other thing I'd like to point out, that the distances on the bottom are a little funky. It starts out with increments of 50 and goes up to increments of 2,500 and 1,000 at the end. This is because this is a combination of different data sets and testing locations, and we just took a number of the best data that we had and combined them into these graphs. Next is what we saw with the 200 kilobits per second chip with the SMA antenna. This also performed to about 2,500 meters before it dropped off, and actually drops off a little steeper than the previous one. Then we have the 200 kilobits per second chip with the U.FL antenna. And surprisingly, this performed twice as well as the previous two. It actually got out to 5,000 meters before it dropped off. But we really knew that this was definitely the maximum distance, because when it dropped off, it's almost a solid cliff drop off that. And then I have the wire antenna here to show you that it really is not made for long range distances. It goes to about 350 meters or so, and then it just begins dropping off, which is kind of what I predicted, that you want to, with this chip, you would have to stay under 400 meters to really get good signal strength and packets. Towards the end of the summer, we were given one additional chip to test out. The Nanotron NanoPan 5375 from Nanotron Technologies in Germany. It was a 2.4 gigahertz chip that was ranged up to 6 kilometers. And the reason that we were really excited about this chip was that it had two really cool features to it. One was that it's reprogrammable. Now, when I say it's reprogrammable, I don't mean that you can fundamentally change the function of the chip. I mean that you can change different parts of it, such as power output or data rates. In fact, you can change the power output of it from negative 15 decibels to positive 20 decibels, and data rates from 250 kilobits per second to 1 megabit per second. And because it looked like this was such a promising chip, we were told to try to test it in a way that simulated what it would be like in space. So we needed to find a testing location that had zero interferences, a nice dip in between them if possible, perfect line of sight, and a good distance from 0 to 3 kilometers. Now, the reason we weren't going further than 3 kilometers is because in space, the two satellites would not be expected to talk with each other beyond about 2 kilometers. So if it could go up to 3 kilometers and still communicate well, this was exactly what they wanted to see. To do this, we field tested them from the top of two nearby mountain peaks, Baldy and Saddle Peaks. It had a perfect line of sight, a really nice dip in between the two, because we weren't going right along the ridge line, we were going a little off to the side of it. And because we were on the top of two mountains, electronic interference was absolutely zero. Unfortunately, it did take us 2 trips to get this data. The first time we went up, we were about 3/4 of the way to the top, and then it started snowing on us. We thought, oh, it's still kind of clear out, we can keep going. Well, we got to the top, and it was just a whiteout. We couldn't see 10 feet in front of us, so we had to give up on that. Luckily, the second time we went up, it was great, and we got really nice results. As you can see here, this is also a combination of different results, and actually 2 different results. From here on to here, this is what we took on Nash Road. So initially, it looked like the chip would only perform to about 1,650 meters, and then it starts dying on us. However, as you can see here on the very end, when we took it up to Baldy and Saddle, it got up to 2.9 kilometers and was receiving over 90% of the data packets, which was what we wanted to see. We didn't want to get anything under 90%, and since this was well over 90, this chip was considered a success. So, in the end, we learned a lot about the process of how Cube satellites and really just space missions in general start from the design, planning, to the building, launching, and maintaining of it in orbit. We also learned how wireless communication devices work, as well as their ranges, strengths, and their advantages and disadvantages, as well as how infrared imaging equipment works and their uses. Any questions?
the reason behind having the two cube satellites take pictures of each other?
That was so that they could identify each other, and in the hopeful near future purpose of taking images of a larger satellite, like when I was saying how they could perform repair missions on larger satellites. Well, if it could accurately take pictures of another satellite, then we could look through those pictures and see if we could identify any problems with the larger satellite or any other object that they're looking at.
So they're just practicing.
Yeah, this was all just a practice test.
Practicing.
And if this mission was a success, it would have represented up to a 10 times price reduction on what normal proximity flights such as this would cost. As well as hopefully, if it's a success, it would reduce the dangers that astronauts have to place themselves in when going on spacewalks or just being in space in general. Because we could have machines take over enough of their jobs.
Huh.
Great.
How did the focusing work when you were taking the pictures in the hallway? When you were putting your camera at different distances and undoubtedly that changed the focus. What mechanism do you have to do that?
Well, with the cameras, we could only focus them to one distance, and then that was it. You could set it to 0 to about 30 meters, or actually no, it could go up to 50 meters, and then that was it. So if you wanted to try to focus it at a different distance, we would actually have to manually change it on the camera and then lock it in, which was actually a really hard and time-consuming process.
So in spaceflight, you'll have a range where you have to get into a range.
Yeah,
where you can take
in space, I believe they were going to probably focus it to about 5 meters or so to get a good distance between 0 and 2 kilometers. Because it's more imperative to see greater details when it gets up closer. At further distances, it's okay if the image is a little blurry, as long as they see a little white cube space, then it's fine.
You talk about communications between the satellites. How do you handle communications between the satellites and the ground? And or have you gotten into that yet?
That actually wasn't our department.
Okay.
Another company or school was dealing with that in our mission, for the mission. The mission was comprised of numerous companies and 2 schools for this mission.
So you just handled the inter-satellite communications?
Yeah, we just did that in the cameras. That's all we were given.
Okay. Do you know what kind of modulation these things use to communicate?
I don't know what kind of modulation. I'm not sure if modulation even is much of an issue up there.
Okay.
Because they don't really have much in the way of interference up there in space.
That's true.
So is there a timeline for the mission, for the overall mission? Like when is there?
Yes, I forgot to say that. The mission, if it's still on track, is due to be launched in the 4th quarter of next year, so sometime between October and December. But they haven't chosen a specific date yet, but I assume that they'll have one by the end of the year.
Is there a launch vehicle selected?
Yeah, it'll be launched on an Atlas rocket out of Texas, or New Mexico.
Yeah, can you say?